Hello and welcome back to the course on machine learning. Today we've got a very interesting topic. Today we're talking about Thompson sampling and the algorithm's intuition. And again, we're going to be using this algorithm to solve the multi-armed bandit problem. All right, so let's get started. A quick refresher on the multi-armed bandit problem. We have several slot machines. Each one of them has a distribution behind it, D1 to D5. We don't know what these distributions are, and we need to start playing these machines and at the same time figure out which one has the best distribution so that we then exploit that best distribution. But it'll take us some time to figure it out, so we need to maximize our return during the process of figuring out. So we have to find that ideal balance or trade-off between exploration and exploitation. We had a few tutorials previously on these things, so we talked about the multi-armed bandit problem in a lot of detail. So if you haven't watched that tutorial, highly recommend jumping into the previous section and watching it there. Also, understanding of the upper confidence bound algorithm will really help you grasp the concepts of Thompson sampling. So if you haven't seen the upper confidence bound tutorial, then I highly recommend checking that out before proceeding with today's lecture. All right, so let's get started. A quick summary of the multi-armed bandit problem is as follows. We have D arms, for example. Arms are ads that we display to users each time they connect to a web page. So by the way, yes, indeed, a modern application of the modern representation of the multi-armed bandit problem is advertising. So when you display ads, that is very similar, or the algorithms that we're going to be applying can be applied to solving that problem where you're displaying ads. So if you go back here, instead of having these slot machines, each one of these is a different ad, and you want to figure out which one of these ads is the best performing ad, but you don't have time to do an A/B test, so you don't have the funds or the resources to do an A/B test. You want to figure it out on the fly. That's when you would apply one of these algorithms that we're talking about in this part of the course. And of course, there's lots of other modern problems that are very similar to the multi-armed bandit problem, and therefore these algorithms are valid for them too. All right, so moving back here. So we've got D arms, for example. Arms are ads that we display to users each time they connect to a web page, each time a user connects to this page. That is considered as a round. At each round N, we choose which ad to display to the user. At each round N, the ad gives us a reward, either 0 or 1. 1 if the ad is clicked, 0 if the ad is not clicked. In the case of the actual bandits, it'll be a monetary reward, so it won't be just 0 to 1, it'll be some value. Our goal is to maximize the total reward we get over many rounds. All right, so that's a quick overview of the problem that we're solving. Then here we've got some very complex looking mathematics and Bayesian inference and all these distributions and posterior probability and other prior distributions and beta distributions and so on. We're not going to delve deep into this right now, so Hadlan will take some time to walk through this slide with you in the practical tutorials, because we're going to be coding this from scratch, well, at least in R, and therefore he will actually walk you through this slide. Our goal for today is to understand the intuition behind all of these things. So we're going to skip this slide and get to the intuition part, and this is the actual steps that you're going to be using in the practical tutorial. So again, Hadlan will walk you through this slide as well. And today we're talking about the intuition. So this is going to be fun. This is some interesting slides coming up, and get ready for a fun ride. So grab your cup of coffee, a cup of tea, and or even some popcorn, and let's get started. All right, so here we've got a scale. The y, or the horizontal axis, is the return the return that we expect to get from a bandit. So we're going to look at a simplified problem. We're going to look at rather than 5 or even 10. We're going to just look at 3 bandits because there's going to be a lot of stuff going on this chart, and I don't want to clutter it up, and we want to keep it as simple as possible just so that we can understand the concept. And then the same thing applies for 5 or 10 or however many machines that you'd be looking at. So here we've got the return, and these vertical lines, just like in the case of the upper confidence bound, we had the horizontal lines. These vertical lines represent the expected return for each of the machines. So each of the machines, out of the 3 machines that we have, each of the machines has a distribution behind it, so that the result, the amount of money that you win per game, is picked as a random value from that distribution. And we're not going to draw the distributions, but basically just imagine a distribution behind each one of these expected values. So this is just the center of that distribution, or the actual expected return from that machine. And we're just visualizing it here, but this is us kind of like looking into the actual machine itself, or like pulling it apart and knowing how it works, or being the designer of the machine. In reality, when you're playing these machines, of course you don't know this. So this is some additional information that will guide us, that will help us understand how the algorithm actually works. The algorithm itself doesn't know this information, right? So this is hidden, but it's just there for us so that we can better understand what's going on. So these are the expected returns, the actual expected returns of each of the machines. And obviously, if you knew this right away, you would say that machine number 3, or the yellow machine, is the best one because it has the highest return, right? It has the highest expected return. You'd always just bet on this one. But again, you don't know this yet. All right, so what happens with this algorithm? Well, at the start, just like with the upper confidence bound algorithm, you don't know anything, right? You have no prior knowledge of the current situation or status of things, and therefore all the machines are identical to you, and you have to have at least one or even a couple of trial rounds just to get some data to analyze. And so let's say that has happened. There's some trial runs for for machine number 1, or the blue machine, and based on those trial runs, the algorithm, the Thompson sampling algorithm, this is where it starts getting different to the upper confidence bound, will construct a distribution, right? So we'll get to this distribution in a second, what it means. But for now, let's just do the same thing for the green machine. And so again, we're just pulling the arm several times, like 4 times, for instance, and we're getting some values, and that are going to be somewhere around, obviously, the actual expected return, right? And based on that, and based on those values, of course, it's probably going to be a bit more than 4. We're constructing some sort of distribution, or some sort of perception of the current state of things. And this is the part where it gets interesting. So the actual meaning of these distributions is not what you might think at first. So these distributions are actually showing us, or they're representing, we're not trying to guess the distributions behind the machine. So the first thing that might come to mind is that, all right, so we've constructed distribution, and so the blue distribution is our attempt at guessing the actual distribution behind the blue machine, right? The distribution that this is the expected return for. And the green is for the green machine, the yellow is for the yellow machine. Well, actually not. That's not the case. We are constructing something completely different, something completely out of this world. We're constructing distributions of where we think the actual expected value might lie. It's very important to understand that. So we are creating kind of a, if you want to think of it that way, we're creating an auxiliary mechanism for us to solve the problem. So we're not trying to recreate these machines. We're recreating the possible way these machines could have been created, kind of in that sense. So let's just solidify that. This is where we think the actual expected values will be. So let's look at the blue one, for instance. We got 4 values, and based on those 4 values, we've constructed this distribution which will show us, which is showing us where is that value mu star. So this is mu star, the actual mu star, but we don't know it, so the algorithm doesn't know it. So it's constructed a distribution trying to guess where this value is. And of course, can't just say it's over here, or it's over there, it's over there. It's saying, okay, there's a very high likelihood it's over here, but it also could be here, it could be here, it could be here. And as you move away, the likelihood drops, but it still could be anywhere in this blue space. Same for the thing for the green distribution. So based on the values that we've seen, the random values that have been selected in the four rounds, the algorithm has created this distribution which is saying that this actual expected return from the green machine is somewhere in this area, and it's most likely to be here, but it could be here, it could be here, it could be here, it could be anywhere. It could be, so basically it's most likely to be here, then it could be here, it could be here, and as you move away, the likelihood of it actually being there drops off. Same thing for the yellow one. So it's very important to understand. So just to reiterate, we are not trying to guess the distributions behind the machines, right? We are doing like kind of a little magic trick, or a little hat trick. Is it? I don't know if it's called a hat trick, but we're trying to do create this perception of the world. We're trying to mathematically explain what we think is actually going on, or what could be going on, and that is important. Also important thing, because this demonstrates that the Thompson sampling is a probabilistic algorithm. The upper confidence bound was a deterministic algorithm where everything was strict. You know, everything was okay. So whichever one has highest upper confidence bound, that's the one we're going to choose, and so on. But here we're creating a probabilistic perception of the world. We're saying, so it's likely to be here, but it could be anywhere in this blue area, and this one could be anywhere in this green, and so on. And you'll see exactly why we've done this. In the next slide, we'll understand how this works. And let's jump straight into that. Let's understand now that this is probably the hardest part, to kind of get your head around what we've created. And now that we've created it, let's see how the algorithm is going to utilize this auxiliary mechanism that we have created. All right, so let's have a look. So there are our distributions. That's where we think. So these are the actual expected returns for each of the machines, but the algorithm doesn't know them. All the algorithm has created are these distributions which allow it to kind of guess where the actual distribution might lie for each of these machines. So what it's going to do is it's actually going to trigger each of these distributions. So like we're in a new round, we have to choose a machine to use. So what the algorithm will do is it will go and call this distribution, and it will pull out a value out of this distribution. And let's say it pulled that value. Then it will pull a value out of the green distribution. Let's say it pulled that value out of the green distribution. And let's say, and then pulls a value out of the yellow distribution. Let's say it's that distribution, that value. And again, it's pulling them so according to the distribution, right? So this is a distribution of values. So basically, it's most likely to pull a value somewhere in this area, then less likely in further away you go, it's less and less likely. But still, it can happen that you can see that this yellow value is actually quite far from the center, but it still can happen that it pulled this value out of distribution. And it can happen that it picked this green value out of the green distribution. Totally can happen. In the long term, of course, it's going to be picking somewhere close to the center, like over the long run. But on a one-off basis, this can totally happen. And so now it's picked these values, and guess what that means? Well, what this actually means is that we have, by doing that, we have generated our own bandit configuration. So we have created this hypothetical or imaginary um, batch of machine, or not batch, imaginary set of machines in our own virtual world, where we're saying, okay, so the actual expected return for the blue machine is this value, the actual expected return for the green machine is this value, and the actual expected return for the yellow machine is this value. So we've created this pseudo world or hypothetical virtual reality in which we have our own three bandits. And now we're going to solve this problem. This problem is very easy to solve. It's obvious how to solve this problem. You just pick this machine, right? Because this machine has the highest expected return out of the three. And obviously, you're just going to go with this machine in the virtual world, in the pseudo reality. And what that means is that now we translate this result into the actual world. In the virtual hypothetical world, we've selected the green machine. So in the actual world, the algorithm will also select the green machine. And what that will do, so it'll basically pull the lever for this machine, right? And what that'll do is actually it will give us a value. So the machine will spit out a value, but that value is going to be based on the distribution behind this machine, where this is the actual expected value of that distribution. So the value is going to be somewhere here, probably close to the actual expected value. It doesn't have to be. Again, there's a distribution behind all this. It could be far away, it could be close, but let's say in this case it's this one. All right, so now this information, this is new information to the algorithm. What it's going to do is it's going to say, okay, so I pulled the green lever, the lever for the green machine. I got this value. So now I have to adjust my perception of the world, right? So I have a prior probability. So these are my, or for the green machine, this is my prior distribution. This is where the Bayesian inference comes into play, or it's already been in play, and this is where adding to the Bayesian inference. So that's our prior probability, prior distribution. Now we've got some new information. This is our new information. We're going to add it in and see how that changes our perception of the world. Well, perception of the world has changed. The distribution has shifted a bit, and it's become narrower because we have more information. Our sample size has increased. Of course, of course, it's not going to increase that much. This is just an example to demonstrate what we're talking about, to get the point across. But that's the point, that every time we add new information, our distribution becomes more and more refined. All right, so now we have a new perception of the world. Now what happens next is a new round, right? Same thing. We're going to do the same thing again for a new round. Again, we generate, or we pick some values out of our distributions. There they are. Now we've constructed we've generated our own bandit configuration in our virtual reality, or in our hypothetical world. Out of these three, we have to pick the best bandit, which is of course the one here, the yellow bandit. And we're going to now actually pull in the real world, pull the lever of the yellow bandit, or the algorithm is going to do that. That's going to trigger the distribution behind the yellow bandit, and that will give us some sort of value. So this is the actual value that we received in the real world. Now we're going to incorporate that value into our perception of the world, and our perception of the world is going to change. It's going to adjust. There we go. Now we're going to do that again. All right, so let's just do this one more time, just so we practice the logic behind all of this. So a new round generates the bandit configuration, right? So this is what we're going to think that our actual expected returns are going to be. Our bandit configuration. This is obviously the best one. We're going to pull the yellow machine's lever. That's going to trigger the distribution behind the yellow machine. It's going to spit out a value in the real world. There's a value, and then we're going to have to adjust our perception of the world again to match or to incorporate the new information. and so on. We're going to keep doing that until we get to a point where we've refined the distributions substantially and the picture looks like this. So they might be refined even more. This one might be more refined. This one might be more refined. But as you could see from there, we slowly will start generating more and more rounds based on the yellow machine. We'll be triggering the yellow machine. So these ones might not even get that refined in the long run, which is totally fine because our point is to get to the best machine, to find it and exploit it as much as we can. So there we go. That is pretty much how the Thompson sampling algorithm works. And as you can see, it is a probabilistic algorithm, and every time we're generating these values, we're kind of creating this hypothetical setup of the bandits, and then we're solving that, and then we're applying the results to the real world. We're adjusting our perception of reality based on the new information that generates, and then we're doing that again. So hopefully this was a interesting tutorial. I find this algorithm very, very cool, and in the next tutorial we're going to compare a little bit the upper confidence bound and the Thompson sampling algorithm, and I can't wait to see you there.